In this video, we're going to talk about linear approximations and differentials. Our objectives will be to find the linear approximation of a function and use it to estimate a value of that function, and to write a differential expression for a function and compare estimates of function values. So let's go ahead and define linear approximations. Suppose f is a differentiable function on an interval I containing a point x equals a. The linear approximation of f at x equals a is the linear function L of x equals f of a plus f prime of a times x minus a for x in a. Visually, let's try and see if I can draw you a graph here that we have a curve like so. And let's put a point here, a f of a. And we have a tangent line here, right there. And this is going to be L of x. This function here is y equals f of x. And so we're going to then have a actual x value over here that we're interested in that's close to a. Call it b right here, and here's the actual value, b f of b, and here's the linear approximation of it, b L of b. And notice that they're very close to each other. The closer that we are to a, the better the linear approximation is, the less error there is here. As I get far away from a, then that approximation really isn't that good anymore. If I were here at c f of c, then c L of c over here, I would probably say this is starting to get to the point where L doesn't really help me approximate what's going on at f anymore, because f has pulled away too far from L. So up close, L of x resembles f of x so much that they are indistinguishable from one another. If we actually think of this curve as a whole bunch of little lines, then this is at this particular segment right here at a f of a, they're the same line segment right there. In math language, interpretation based on what we've already learned, we want to find the equation of the tangent line of f equals, in this example here, the square root of x at x equals 1. So linear approximation, we want to find the equation of the tangent line of f of x at f of x equals the square root of x at x equals 1. So we already know how to do this. We're going to find the derivative, f prime of x equals 1 over 2 root x. We've done that before, but to show you again, this is x to the 1/2. So f prime of x is 1/2 x to the 1/2 minus 1. F prime of x is 1/2 x to the negative 1/2. F prime of x is 1 over 2 x to the 1/2, which is 1 over 2 root x. So f prime of 1 is going to be 1 over 2 root 1. So it'll be 1 over 2 times 1 is 1/2. I also need to find f of 1 is going to be the square root of 1 is 1. So I have the point 1, 1 that I'm interested for my a f of a. So I have y minus y1 is equal to m times x minus x1. Y minus 1 equals 1/2 x minus 1/2. Going to add 1 to both sides. And y equals 1/2 x plus 1/2. So my L of x here is equal to 1/2 x plus 1/2. Now that I know that, I can actually find the approximation of, oh, well, we just did that. So let's just do it this way. L of x is equal to f of a plus f prime of a times x minus a. That's really the same thing that we were doing. So our L of x is equal to f of a was 1 plus f prime of a was 1/2 x minus 1. L of x is equal to 1 plus 1/2 x minus 1/2. L of x is equal to 1/2 x plus 1/2. And we already did it the old way. See previous page. So if we wanted to see a picture here of this, you'd get a much better picture with something like Desmos. But I'm going to show you, here's the square root function. We've got the point 1, 1 on there, and we've got this line here that's going to go through 0, 1/2, and it's going to have a slope. I'm going to do my best to draw this as a tangent line. Just bear with me. It's about the best that I can do. Again, you get a better picture with a graphing utility, but let's say that that point there, for the sake of argument, is 0, 1/2. And this point here is 1, 1. And the slope of this graph is 1/2. This L of x is equal to 1/2 x plus 1/2. And at points that are close to that are close to 1, 1, like if I wanted to approximate the square root of 2, let's say, and let me just grab a color here where I can do that. 2 would be somewhere over here. And so this is 2 root 2, and 2, if I stick it in here, 1 plus 1/2 is 1.5. That's not a terrible approximation. This is 1.41 something or other. So this right here, this distance is our air. And that air gets bigger and bigger the further and further that I get away from 1, 1. All right, let's go ahead and look at another example. Find the linear approximation of f of x is equal to the 5th root of x at x equals 32 and use it to approximate f of x at x1 equals 33 and x2 is equal to 1. So first thing we want L of x is equal to f of a plus f prime of a times x minus a. So let's find the equation of f prime. So f prime, let's see, let's plug some stuff in here. L of x is equal to f of a. So this is going to be f of 32 plus f prime of 32 times x minus 32. Just a second here, f prime of x is 1/5, x to the negative 4/5 is equal to 1/5 times the 5th root of x to the 4th, or it's probably better in this case to do the 5th root of x raised to the 4th power. So f prime of 32 be 1/5 times 2 to the 4th. 1/5 times 16 is 1/80. Perfect. So f of 32 is 2 plus 1/80 times x minus 32. This is part A. So L of x is going to be 2 plus 1/80 x minus 8 goes into there 4 times, into there 10 times. This is going to be 2/5. And then multiply by 5/5. L of x is going to be 10 minus 2 is 8/5. 1/80 x plus 8/5. All right, so that is my equation of my tangent line. That's my linear approximation at x equals 32. I'm going to use that linear approximation to approximate what the 5th root of 33 is. And so that's going to be 33/80 plus 8/5. This is 16. Yeah. Multiply by 16/16 here. 33 plus, this is 128/80 is 161/80 is 2 1/80. So my difference, here, we would expect this to be really, really close. Let's see. Now we're going to, let me just grab my calculator here and show you what the difference is to a few decimal places here. So just a second to load that up and pull it over to the side for you. While I do that, let's go ahead and find the approximation for the 5th root of 1, which we know the 5th root of 1 is 1, but we're going to get a terrible approximation for it. So L of 1 using this model that we just got here is going to be 1/80 plus 8/5 is 1 plus 8 times 16/80 is 1 plus, let's see, 128 over 80 is 129 over 80. I'll tell you what that is in just a second. So this one, 161 over 80 is approximately 2.0125. That's actually exactly what it's equal to. And then 129 over 80 is equal to 1.6125. Very good. Now let me tell you what the fifth root of 33 is to 5 decimal points. So the fifth root of 33 is about 2.01235. Okay. And so now I want to find the difference between that and 2.0125. Let's call this 24. So that we go to 4 decimal places like that did. All right. My error here, remember error is absolute value. The absolute value of negative 0.000153383. So my error is about 0.00015. Let's call that 2. When we round to 4 decimal places, it's very, very, very good because I stayed close to my original value there of fifth root of 32. So now let's look at, I know that the error here is going to be absolute value of 1.6125 minus 1.0000. This is 0.6125. That error is not so good because I went so far away from where my approximation was based off of the fifth root of 32. I'm too far away. So I would need to set up a linear approximation that was closer to 1 if I wanted to get a good approximation of what the fifth root of 1 was, which I don't need to get an approximation. I know exactly what the fifth root of 1 was, but I know exactly what fifth root of 32 is. Fifth root of 33 is really close. I got a really good approximation there within 2 10,000ths. That's good. All right. We're going to use this idea now with something that we call differentials. And we're going to use it to help us find things like propagated error and things like that. So first, let's make sense of the notation. Y prime is equal to f prime of x is the same thing as dy dx. So dx and dy are called differentials. And they stand in the place of infinitesimals. So given a function y equals f of x, we define two variables, dx and dy, where if we draw a slope triangle here, here's x, and here's another point here. Here's where our linear approximation is based, right? Then here's a point that we're trying to estimate, and there's that point on the line. And so this distance right here We call this dy. We call this distance here dx. Now dx is exactly the same as delta x, but this entire distance here is something that's actually called delta y. And you can see that dy and delta y are close to each other, but they're not exactly the same. They're off by that little bit of error, but dx and delta x are exactly the same. There's no error between them. So that's our whole idea of what we're going to do with differentials, is that we're going to let, we're going to say dx is exactly equal to delta x. And when we do that, then we're going to say dy is about the same thing as delta y, and we get an approximation. So dy depends on dx, dy dx. The ratio of those two things is equal to the slope of the tangent line. So what we're going to do now is that we're going to treat this in some ways like it's a fraction, even though it's not necessarily a fraction. It is a rate of change, but we're going to multiply both sides by dx, and we're going to use the equation dy is equal to f prime of x dx, and then we're going to say that delta y is approximately f prime of x delta x. The value of dx is usually very small. This is what we call an infinitesimal. Decimal, I think I spelled that right. It's related to the word infinity, but it's the small version of it, so it's an infinitesimal. The value of dy depends on the value of dx. We said that already. Dy equals the approximate change in y equals f of x when x is incremented by dx. So this is a fundamental interpretation. I already drew you the picture of that. That we need to know that it's an approximate change, that look at dy is about the same thing as delta y as long as I stay close, and close is a relative term here, close to x, because it depends how rapidly f of x is changing, how close I need to stay to x to get a good approximation. So as dx gets small, the error between delta y and dy will, so smaller, will also get smaller. The closer I am to x, the better the approximation dy is for delta y. All right, let's consider the function f of x is equal to x squared. Find an expression for dy and write expressions for dy at x equals 1 and x equals -3. So first things first, f of x is equal to x squared. I need to find f prime of x is equal to 2x. That means dy dx is equal to 2x, so dy is exactly equal to 2x dx. This is an exact equation as long as I have the differentials on both sides. Now at x equals 1, dy is exactly equal to 2 times 1 times dx, or dy is equal to 2 dx at x equals -2. dy is going to be 2 times -2 dx, so dy will be a -4 dx. Those are exact equations there. I've done no approximations so far because I have not used dy to approximate delta y yet. Let's go ahead and look at my picture here. And looking at x equals 1 right here, have a tangent line here like so, and that I have this slope triangle right here, and this is dx, and this dy is going to be exactly equal to 2 times dx, whatever dx is. Because the slope triangle, because the slope over here is equal to 2 over 1 times my 1 that's right there. All right, so now if I'm over here at x is -2, I'm over here, that slope is steeper, more negative here. Have this slope triangle here where I have, let me try to draw this a little better. Here's -2. Let me go out to somewhere over here. Right, and then let's say like this. There's my slope triangle. And so this is -2. And this is -2 plus dx. This is dx. And this side over here, dy, is equal to a -4 dx. All right. There it is. So that's what that would look like based off of those 2 points that are there. This slope here is negative. This is positive. That's why that's negative when this is positive. This is positive when that's positive. dx, we're going to try and keep it positive when we can. But in both cases, I'm going to the right. So dx is positive. But here dy is negative because I'm going down and to the right because I have negative slope. All right, that's it for this video. We'll come back next time and we will talk about indeterminate forms and L'Hopital's rule. We'll see you for the next video.